All right, let's talk through the falling chain problem. So this is just from the key that's online, but I thought I should talk you through it. So we're looking for the force as a function of x being the distance each little chain link has fallen. Some of the chain doesn't have to fall at all, right? So it's like x is 0, and some of the chain has to fall a distance L, right? But x varies from 0 to L. The force that the ground has to support is really two things. One, it has to support the weight of the chain that is laying on the ground, and it has to actually stop the chain that's falling, and each little link is falling at a different velocity. And so each little link has a different amount of momentum, but that momentum has to be thrust upwards. And so here's the basic of the equation, right? So the force of the table has to be the weight of the chain, it has to support it, and then it has to provide some upward thrust to stop each piece. Okay, so let's go over this part first. This is probably the easiest of the parts. The weight of the chain is some fraction of the total weight. The total weight is just mg. And then if you think about x over L, x being how much of the chain has fallen, if 10% of the chain has fallen, then the table is supporting 10% of the total chain, right? X over L is just a fraction, right? Just a number, just a ratio, a percentage. So you're taking that percent times mg. For instance, if x is 0, then nothing is fallen yet, right? X is this distance, right? Nothing has fallen. Then the table doesn't support any of the chain, and so then this term is 0. Once x becomes L, then this is 1, and then the weight of the chain on the ground is all of the chain, which is just the full mg. Once x is half of L, then you're supporting half of the weight, and so then this force becomes half of mg. Okay, so the weight of the chain on the ground, is now a function of x. Okay, that's step 1. Step 2 is to look at the thrust. And we know, based on our examples on the board, that thrust is dp, meaning the change in momentum over a time period. And we're going to break this down just like we would if we were looking at like a garden hose question. Delta m over delta t times the velocity, meaning how many kilograms of a chain am I stopping, how fast am I stopping it, and then what's the speed of each one of those links. Okay, this is the hard part up here. Delta m. Okay, so each small part of the chain has a distance, meaning a length, of delta x. So then how much does each little delta x is a distance, how much does each one of that delta x have in mass? Well, it's the same thing. Delta x is some fraction of the total length, so then delta m is some fraction of the total mass. Delta m is the mass of each little link. Again, think of that again. These have to be in the same proportion. Delta x versus L is delta m versus m, and I just multiply the m over, right? This is the fraction of the mass that makes up that link. So then we have an equation then for delta m. So we're going to take that and put it in down here for delta m. Delta x m over L is the same thing as delta m. Okay, now the velocity. Normally we talk about like the exhaust velocity, but this is just the same thing, except we're stopping something instead of starting something. But the velocity is easier. We can just use energy, right? All we have to say is mgh equals 1/2 mv squared. But each one of these links don't fall a height h. They fall a different height. Some of them fall none, 0. Some of them fall L, but they all vary, meaning they're a function of x. And so the velocity of each one of the individual links is the square root of 2gx, meaning mgx equals 1/2 mv squared. And I just solved for v. So now I have the velocity of each one of the links as a function of x. And then I notice down here, what is delta x over delta t? Well, that's also velocity. So then this term turns into m over L v squared, v times v. Then I made a substitution. I put the v that I found over here for energy in for v squared. Squaring that just becomes 2g x m over L. And then I put that back into here. So then the force that the table has to do is the weight of the chain on the ground plus the thrust, and I've rewritten the thrust as a function of x, but then this is just a 1 mgx over L plus a 2 mgx over L, and so you get 3 mgx over L. And then if, so that's kind of really your answer. I didn't actually simplify that. 3 mgx over L. And then I looked at the limiting case. What happens when the total chain is actually falling on the ground? Meaning if x equals L, then the force that the table applies at that very moment is actually 3 times the weight of the chain. Okay? So there are some big conceptual pieces that you should know, and that's, I say, with this statement. That statement is 100% like, have to understand that the force of the table supports the weight of the chain. So the chain that's down here, you have to support the weight. It's not the full weight of the chain. It's some fraction of the total length is on the ground, so you're supporting that. And then instead of having like a rocket ship throw stuff out, meaning take it from 0 to some velocity, you're just taking it from a velocity v and you're stopping it. So it's still the thrust equation. You're just stopping something instead of starting something. The thrust that we talked about in class is dp, delta p over delta t. We can rearrange delta p as delta m and v. And then this is the hard part here, that the mass of each chain length is somehow related to the distance of each chain length. And really, it's more like a density thing. Make a couple substitutions, and then boom, we have that as our final force equation. Okay, we can talk about this in class, but I thought, for the people at home, if you're trying this problem and you wanted to kind of have somebody talk you through the key, that this would make sense.